Good morning, everyone. This is thermodynamic lecture number 5. And in the previous class, what we had done, we had discussed the different thermodynamic processes and we had solved some questions based on that. Do we remember those? The questions that we had done, the things that we had discussed, do we recollect it? Yes or no? Yes. Well, what I'll do is, since this is a very important topic and I'm expecting a lot of questions from this side, I'll do 2 or 3 more so that we are more ready with what our understanding is. So I'll solve, because there are no questions on the diagram, so we'll solve 2 or 3 questions on that diagram. When you have a PV graph and then they ask you questions, so what we are going to do is solve those questions, because I did not find them in the previous year thing, and I thought that we should be solving them. 2 or 3 questions, again they are taken from your exercise only, but we are solving them so that you have an idea about the graph wala questions, because I'm expecting that you will get a graph wala question this year, maybe more than that. Okay, so here we start with the first question, and this is the first question for you. This is from level 1. Question number 1. Can you tell me the answer for this one? A thermodynamical system goes from one state to another state. The external work done is given by. I hope you can see the entire question. Or I think saw the recording and it was a bit. I'll just make it bigger so that you can see the question. How do I make it bigger? Again, this will be cut from here. Okay, you can see this entire question, yes or no, on the screen. You can see the question on the screen, yes or no? The entire question. Okay. So what is the answer for this one? A thermodynamic system goes from one state to another state. What is the work done in this process? And the answer is A, B, C, D. The answer is not 2. The answer is not 1. The answer is 0. How do you get 0? This is a process which is done at constant volume. You cannot find any area under the graph, and hence the answer is 0. Do we understand this? Anyone understands this in the class? Okay. Then I'll bring you the next one. Again, I'm just concentrating on 3 or 4 questions based on graphs, because I strongly feel that you will get these questions in the exam. This one, question number 5. An ideal monatomic gas is taken along the cycle A, B, C, D as shown in the PV graph. What is the work done in this cycle? I am getting one as answer. How do I get work done? I simply have to find the area of this region. How can I find the area of this region? This is simply a rectangle. I will have to find out this length. How do I find out this length? This one is 2V, this one is V, so this entire length becomes V. Then I must find out this length. How much is this length? How much is this length? This is P, this is 2P. So this length becomes P. I just have to find the area of this. This is P multiplied by V. The answer becomes PV. Do we understand this? Okay, I'll do one or two more because I feel, again, I'm repeating myself, that this question is going to come. This one. Let's see who gets me the answer for this one. A thermodynamic system goes from state A to state B as shown in the figure. What is the work done in this process? How do I get this? To find the work done in this process, I have to find area in this graph, area under this graph. And what is the area under this graph? Area under this graph is this hash that I have done. You have to find out the area of this thing. How much is the area of this thing? How much is the area of this thing? To find the area of this thing, I must find out this length. How much is this length? This is 2V and this one is V. So this becomes V. I have to find out this length. One point is 0, other point is P. So the length is P. One length is P, other length is V. The area becomes PV. Do we understand this? That is how you find out area under this graph. Please listen and solve these questions carefully because, as I have told you, one of these questions will be there in the examination hall. One of these would be there in your examination hall. Let me see who gives me this. This is question number 4. Again, we are concentrating only on questions which have graph, nothing else. An ideal gas is transformed from state A, P1, V1 to state B, P2, V2 through the path AB. In this process, what is the work done by the gas? You are given 4 options. Which is the correct option? Area A, B, C, D, A. We have to look at the diagram carefully. I hope you can see the diagram. What is the correct answer? I think this point would be E and this point would be F. Okay. Anyone? And the answer is 1. It is this area that I am shading right now. It is this area. This is the area under this graph. So you have to find out this area. How much is the area? Area from A to B to C to D and back to A. This is the area that we have to find out. And this is the area that we have marked. The only option which matches this area is option number A. I hope we are understanding this. Okay. Again, only questions based on graph, and this is the next one. In the indicator diagram, remember whenever someone says indicator diagram, an indicator diagram is nothing but a PV graph. In the indicator diagram, the work done along the path AB from A to B. You have to tell me what is the work done. Pressure is given in Newton per meter square. Volume, I think, is given in meter cube, not mentioned here, but it should be in meter cube. So, what is the answer for this one? No one knows the answer from A to B. To find out the work done from A to B. To find out the work done from A to B, you have to find out this area. I think you are good enough to find out this area. How much is this area? It's a rectangle. So you have to find out this length. I understand that you understand that this length is 1 meter cube. Then you have to find out this length. I understand that you understand that this length will be 20 Newton per meter square. You just have to find out the area. So 20 multiplied by 1, answer is 20, but they are given two options. One is plus 20 and the other one is minus 20. Whether this is positive work or this is negative work from A to B, that is the only thing you have to understand. Is it positive work or is it negative work? It will be positive work. Why it will be positive work? Because volume from A to B is increasing. Do we understand this? And hence the only option which is correct, which I am going to mark with red, is option number B. Option number B is plus 20. Option number C is minus 20. If I talk about from B to A, the volume was decreasing. So from B to A, it is minus 20. But from A to B, it is plus 20. Do we understand this? Yes or no? Okay. Let's see what comes up next. And this question has an extension. So I'll get to the extension as well. And it has a subordinate question. I hope you can see that subordinate question. And the subordinate question is, in the above problem, work done along the path B to C is how much? That's the subordinate question. What is the work done along the path BC? Talk about BC. This is the path BC. This is B and this is C. How much work is done from B to C? And the answer is A, B, C, D. What is the answer? I hope you have seen the question. Yes or no? And the answer is A, 0. Why it is 0? There is no area that you can make under this line BC because this is a line which is parallel to y-axis. The volume is constant here. Do we understand this? The volume along the path BC is constant. It's a straight line parallel to y-axis. You cannot find out any area in this region. And therefore, work done from B to C is 0. Do we understand this? Now, if I could have changed this question and I could have made this question like this, like what? So what I'll do is I will just take everything out and I will just make it bigger. Now, if I could have changed the question and put the question in this way, the first question that we did was work done from A to B. The second question that we did was work done from B to C. The third question that I'm putting to you right now is what is the work done in the entire cycle? What is the work done in the entire cycle? The first question was A to B. The second question was B to C. The third question that I'm putting right now is what is the work in the entire cycle? And I'm waiting for your answers. What will be the work done in the cycle? When I say cycle, I mean from A to B, B to C, and C to A. So the cycle will be called as A, B, C, A. What is the work done in the cycle A, B, C, A? First of all, tell me, will it be positive or will it be negative? 1 for positive and 2 for negative. Will it be positive or will it be negative? One for positive, 2 for negative. It will be 2, it will be negative. Why it will be negative? Because if you look at this cycle is going anti-clockwise. It is opposite to the clock. And therefore, this work done would be negative. Do we understand this? Remember, clockwise work done in a cycle, clockwise cycle, it is positive. Anti-clockwise cycle, it is negative. That is one part of the question. The other part of the question is how much is the work done? How much is the work done? What is the answer for this? To find out this work done, you have to find out the area of this triangle. And I hope you know how to find out the area of this triangle. It is half multiplied by base. Base is this length. And you can understand how much is this length. This is 1 meter cube multiplied by 1. Multiplied by the height. The height is this much. And I hope you understand how much is this much. It is nothing but 20. So the area will become 10. But the work done will become minus 10 joule. Why minus? Because this is an anti-clockwise cycle. Do we understand this? So this is how questions are framed. And more often or not, questions will be in this class. That is why I have done questions on graph, because I thought that we have not done enough question on graph, and that is the reason we are doing this. Okay, one more question on the graph. I think we have done this. So let's not do this. Okay, we have done this one. Okay, this one. Now this is level 2. This is supposed to be very difficult. Tell me whether you can do this. 4 curves A, B, C and D are drawn in the adjoining figure for a given amount of gas. The curve which represent adiabatic and isothermal changes are which one? So first one is adiabatic. Which curves represent adiabatic process? The second is which curve represents isothermal process? Which one is adiabatic? Which one is isothermal? Now you can have more than one option correct here. Now if I look at this graph between A and B, which one is adiabatic? The steeper one is adiabatic. So B is adiabatic, yes or no? B is adiabatic and A is isothermal. So this is the correct option. This is one of the correct options. If I look at the curve C to D, the steeper one, remember, the steeper one should be the adiabatic curve. D is the steeper one. So D and C respectively would be the answer. But again, you'll have to understand that this curve is not possible for an adiabatic process. Because remember, in an adiabatic process, it could be adiabatic compression or it could be adiabatic expansion. And we have covered both of them. And whenever we covered both of them, I gave you the diagram. Adiabatic curve or isothermal curve have negative slopes. When I say negative slope, if pressure increases, volume has to decrease. If pressure decreases, volume has to increase. So these curves are not possible. And therefore, the correct answer is only option number D. Now, this is a very difficult question which will never come. I have just done this so that you have an understanding of how difficult question look like. Now I'll do one more. I've seen it here. Somewhere here where it's gone. We'll do that and I think we would be enough. I think we have done this question, but this is just to recap what we had discussed. This is question number 157. During isothermal, isobaric and adiabatic process, work done for same change in volume will be maximum for. I think we have done this. In which case the work done is the maximum, A, B or C, and which process is which? And the answer is B. The most of the work done is in process A, which is isobaric. Then it is B, which is isothermal. Then it is C, which is adiabatic. So remember these questions. Whatever we have done, I can assure you the question that you will find in the examination hall will be one of these questions. It cannot go beyond this. I have full faith that it cannot go beyond this. So I will not go any further. Instead of going any further, we will move ahead in life and we will move to the next heading. And you might find questions from this topic straight away coming into your exam. And the next heading is free expansion of gas. I hope you can see this. Let me see how you see it. Okay, free expansion of a gas. Now, what do you mean by free expansion? Free. Nothing in this universe is free. But in case of expansion of a gas, we have a term which calls it free expansion. Now, whenever I talk about free expansion, it is expansion against vacuum. What do you mean by expansion against vacuum? If we have a gas in a cylinder we normally have a piston. This is my bottle. This is a cylinder. In this cylinder, I have a piston. A piston is something which can move up and down or left and right. Now, if one side of the piston you have vacuum, there is no air, no gas. Only one side you have gas or air. And if you allow that gas to expand, that expansion is known as free expansion or expansion against vacuum. Do we understand this? Expansion against vacuum. If one side we don't have any gas, that is known as expansion against vacuum. Now in expansion against vacuum, the work done by any gas is zero and there is no heat exchange between the system and the surrounding. For free expansion, work done and heat given is always zero, whether the gas is ideal gas or whether the gas is real gas. Do we understand this? Please note it down. Note it down because you will have a question on free expansion, so note it down. In a free expansion of a gas, there is no work done and there is no heat exchange. In the free expansion of a gas, there is no work done and there is no heat exchange. Have you noted it down? See, the questions that come in the exam, they are more on information based rather than your numerical base. Numericals are very simple. The information based questions are the question where you will get caught. They might be based on theory, they might be based on simple facts. So you must remember all these facts because these facts will help you score heavily in the exam. Have you done this? Shall we move ahead? Okay. Now, here there are things explained here, but what we got to understand here is there are two types of gases that we deal with, ideal gas and real gas. Don't have to understand everything. For an ideal gas, this free expansion can be adiabatic as well as isothermal. When I say isothermal, the change in internal energy is zero for an isothermal process. That means the internal energy remains constant. That means the temperature remains constant. So, for an ideal gas, this free expansion is going to be two types. It would be adiabatic. There is no exchange of heat. It would be isothermal as well because there will be no change in the internal energy. But for a real gas, it is only adiabatic because the internal energy changes, the temperature of the gas changes, and this is a very important point that I have told you. For real gas, free expansion is adiabatic and isothermal. In short, for real gas, free expansion is adiabatic. Please note this down in your notebooks or sheet or whatever you are doing. I'll give you a minute to do that. Have you noted it down? Okay. Now, the next thing is drawbacks of FLOT, FLTD, first law of thermodynamics. What are the drawbacks? You must remember these drawbacks. The first drawback is it does not tell you how much amount of heat, how much part of the heat is converted into work. For different processes, different amount of work is done for different amount of heat. So it does not give you any information. It does not give it is only telling you delta Q is delta U plus delta W. It does not tell you how much is delta W and how much is delta U. And the most important point which you must always remember, it does not give the direction of heat flow. Or if I talk more generally, it does not tell you which process is possible and which process is not possible. First law of thermodynamics, please mark my words and note it down, does not tell you which process is possible and which process is not possible. It's just law of conservation of energy. It does not tell you which process is possible and which process is not possible. Are you paying attention, everyone? Are you paying attention, everyone? First law of thermodynamics does not tell us which process is possible and which process is not possible. How do I illustrate this? I will tell you a process and do see what is possible and what is not possible. This is a pen in my hands right now here. Now what I'm going to do is I'm going to drop this pen. When I drop this pen, what happens? Right now this pen has potential energy. Right now this pen has potential energy. I'll just stop the share and probably show you on bigger screen. This pen is here. It has potential energy. This is ground. Now when I drop this pen, what happens? Obviously I did not hear any sound. But when I drop this pen, what happens is the entire potential energy is converted into other forms of energy. Now if I make it drop on this table, you will hear something. I hope you can see this. Let me switch off the fan, and when I drop this, did you hear the noise? Yes or no? Yes. So basically what has happened, when this pen got dropped, you can hear some noise. Some part of this energy got converted into heat. Some part of this energy got converted into noise, and my pen is gone. So this is the pen. I drop it. You hear noise. Some part of the energy which was potential energy converted into noise. Some part of energy got converted into heat. Now this is a simple process. Anyone can do this. Hold this pen, drop it. Noise will come. Some part of the energy will be converted into heat energy. Now look at the reverse process of this. What will be the reverse process of this? I have this pen on ground. I make some noise and I heat it up. Will it go up in air? No, it will not go up in air. If I make some sound and if I heat this up, it will not go back in air. This process is easily possible. I have this pen, I drop it, this process is possible. But if I heat this pen and give it some noise, some sound, this is not going to go up. So there's only one way in which this process is possible, and that way is when I hold this pen, I drop it. First law of thermodynamics tells us that both the processes are possible because energy is conserved in all the cases. And that is why it does not tell us which is the correct process and which is the wrong process. Do we understand this? Yes or no? The way that we say this is, it does not give us the direction of heat flow. It does not give us the direction in which a process can happen. So this is the basic flaw of first law of thermodynamics. It does not give us the direction of heat flow, or it does not give us which process is possible. Do we understand this? Then the obvious question is, there must be something that will tell us which process is possible and which process is not possible. So there must be some other law that tells us which is the process that is possible. There must be some law which tells us, okay, when you drop the pen, you will have the noise, but when you create noise, the pen will not go up. There must be some law which tells us which is the correct process. And what is that law known as? Which tells us which process is possible and which process is not possible. What is the law that tells us this? You have not done thermodynamics in chemistry? No? Okay. So you have no idea about which law tells us the direction of process, which process is possible. And that, my dear friends, is the second law of thermodynamics, SLOT or SLTD. The second law of thermodynamics tells us the direction of process, or it tells us which process is possible or which process is not possible. Instead of calling it as direction of process, we can now call it direction of heat, because we are dealing with thermodynamics. It tells us which process is possible, which process is not possible. And there are two ways in which you can demonstrate or you can express this law. The first statement is known as the Kelvin-Planck statement of second law of thermodynamics. The second statement is known as Clausius statement of second law of thermodynamics. Both of them are saying the same thing, but a bit different. What does Kelvin-Planck say? It states that in a cyclic process, total heat cannot be converted into work. It is basically talking about heat engine. So, what does Kelvin-Planck statement say? That you cannot create a heat engine. You cannot create a heat engine, and I hope you are writing it. You cannot create a heat engine which can convert the entire heat into entire work. And I've told you that previously. It is not possible that I am an engine, I take heat, I take 100 joules of heat, and I convert 100 joules of heat into 100 joules of work. That is not possible. This is Kelvin-Planck statement. Do we understand this? Complete heat cannot be converted into complete work. A heat engine which has an efficiency of 100%, it is not possible. Do we understand this? A heat engine which has an efficiency of 100% is not possible. This is Kelvin-Planck statement. So there are number of ways in which I can say this, and I hope that you are writing this, because I am not going to write it. You are going to write it while I dictate it. So everyone write it. Kelvin-Planck statement. There are different ways in which I can state the Kelvin-Planck statement. The first way is what is written in the sheet. It is not possible in a cyclic process to convert entire heat into mechanical work. Please note this down. I don't see you guys noting down. So you must be supercomputers that you have already noted it down. The first way is, in a cyclic process, total heat cannot be converted into total work. That is the first way. Now write the second way of Kelvin-Planck statement. No heat engine can convert total heat into mechanical work. So instead of cyclic process, you just use heat engine. No heat engine can convert total heat into total mechanical work. The third way of writing it is efficiency of heat engine. Efficiency of heat engine cannot be equal to 100%. You cannot make a heat engine in this universe which has an efficiency of 100%. This is how you can state Kelvin-Planck statement in 3 different ways. Have you noted this down? If you've noted this down, then you can come to the next statement, which is known as the Clausius statement. Now, Clausius statement is given for a refrigerator. The refrigerator or fridge that you have in your homes. Clausius statement is regarding a refrigerator. Now again, Clausius statement can be understood in 2 or 3 different ways. And I will tell you what those ways are, and I hope that you are writing it. The first way to understand Clausius statement is how it is written. It is impossible to have net heat flow from low temperature to high temperature. Heat cannot flow on its own from low temperature to high temperature. Are we noting it down? What is the point of discussion in the class? I hope we are not discussing quantum physics there. Okay, please note down the first statement of Clausius. It is impossible to have heat flow from low temperature to high temperature. Heat cannot flow from low temperature to high temperature. Are we noting it down? Please note it down, beta. This is for your own good. I am not going to get anything if you become doctors. Definitely, I am not going to come to your clinic or your hospital, because I know that all of you have got short-term memory losses. You will lose a scissor in my stomach, and I will face it for my entire life. Just joking. So the first way of writing this Clausius statement is heat cannot flow from. Heat can't flow from where to where? Heat can't flow from lower temperature to higher temperature. Heat cannot flow on its own from low temperature to high temperature. It can flow on its own from high to low, but it cannot flow on its own from low to high. That way it tells us the direction of heat flow. Heat can only flow from high to low. And that is why it tells us, that is why second law tells us which process is possible and which process is not possible. Do we understand this? Do we understand this? Okay. Heat cannot flow from low temperature to high temperature. But if I want to make heat flow from low temperature to high temperature, this is what a fridge does, a refrigerator does. If I want to make heat flow from low temperature to high temperature, some work needs to be input. Work needs to be done. Work or energy is to be input. For heat to flow, from low temperature to high temperature. If I want heat to flow from low temperature to high temperature, if I want to cool down something from low temperature to, if I want to cool down something, things in your fridge are getting cooled down. What is fridge doing? It is taking heat from lower inside the fridge and throwing it outside from low temperature to high temperature. It is taking heat from inner, throwing it outside. Inner, outside. So it is making heat flow from low temperature to high temperature. Do we understand this? Heat cannot flow from low temperature to high temperature. If I want heat to flow from low temperature to high temperature, some work needs to be input. Now, similar to what we have for heat engine we have efficiency. in refrigerator. Okay, I can write this like this also. No fridge can work. No fridge can work without power. So when the current goes off in your house, the fridge stops to function, because the function of the fridge or the refrigerator, some people call it heat pump. So the other name for this fridge is refrigerator or heat pump. It is pumping heat out, pumping heat out, pumping heat out. AC is also doing the same thing, pumping heat out, pumping heat out. No fridge or refrigerator or AC or heat pump can work without electricity. When the electricity goes, it stops. We have a term known as COP. This COP is known as coefficient of performance. How your fridge is performing, coefficient of performance. This is same as the efficiency of a heat engine. What is a heat engine? Heat engine is an engine that converts heat into work. Any engine of any bike, any car, any plane is a heat engine. It is converting heat into work. The opposite of that is a heat pump or a refrigerator. It is converting work into heat. Not exactly work into heat. It is inputting work and making heat to flow. The coefficient of performance of a heat pump cannot be equal to 1. Please note these points. Please note this point, because second law of thermodynamics in a question can be asked in any of these points. If you understand these points, that means you have understood second law of thermodynamics. That means you have understood from where to where heat can flow. You have understood that this process where a pen is falling is possible, but when I'm making sound, this pen will not go up. Heat can only flow from high to low. So this is high, this is low. Only this process is possible, high to low. The other process is not possible. That is second law of thermodynamics, stated in a very, very simple and understandable form. Do we understand this? Please note this down. I'll give you a minute to note down all the 4 statements. Have you noted this down? Okay. Then the next heading, since we were talking about the Kelvin Planck statement and we heard the term heat engine, the next heading is a heat engine. Now, what is a heat engine? Everything that gives you power is a heat engine. Everything that is burning fuel is heat engine. What are the three components of a heat engine? Heat source, from where it takes heat. Now, if you think about a diesel engine, whenever diesel burns, it produces heat. If we talk about petrol engine, whenever petrol burns with a spark plug, it produces heat. That is the source of heat that gives this engine the heat to do work. Do we understand this? So every heat engine has a heat source which produces heat, which gives us heat. This heat source gives it Q1 amount of heat. This heat source gives it Q1 amount of heat, and I hope you are drawing this simple diagram. Remember, this is not a pravachan that you see that a Babaji is sitting there and you are all watching pravachans and enjoying your life. Hare Rama, Hare Krishna. This is not how physics is learned by watching a pravachan and getting involved in bhakti. It's not that you have to write. In a pravachan, you don't write. In a pravachan, you only listen to a pravachan. Right? So please write. So I hope you can see that this heat engine has a heat source which gives it Q1 amount of heat, and this is at a temperature T1. I hope you have noted this down. It gives heat Q1 amount of heat at temperature T1. Then you have a working substance. This working substance is your air or gas or anything which undergoes a cyclic process. Remember, this working substance undergoes a cyclic process. It moves in a cycle, starts from state A, then B, C, D, and back to A. It undergoes a cyclic process. In this cyclic process, it gives out an amount of work W. For example, in an engine, in a heat engine, in an internal combustion engine, in a diesel engine, in a petrol engine, you burn fuel, that makes the piston go up and down. That piston ka motion up and down is your work ka output. Do we understand this? Engine, you are burning fuel and the piston is moving up and down. Because of this piston moving up and down, your wheels is rotating. That is the work output that we are getting from burning this fuel. Now, if you can understand, every cycle, every bike, every car has an exhaust pipe. Have you seen that exhaust pipe? Some amount of heat or smoke or carbon, it goes out of that exhaust pipe. Yes or no? That is your sink where you give the rest amount of energy back. So you give an amount of energy Q2 back, which is at a temperature T2. This is known as the sink. So your petrol burning is your heat source. Your wheel rotating is your work, and whatever goes out of that exhaust is your Q2, which is gone out of sink. I'll give you 1 minute to draw this diagram and write everything written in the diagram. A minute. This is the simplest way to understand a heat engine. You only need to understand this much, nothing else. Have you noted it down? Have you drawn the diagram? Yes or no? Okay, then we just understand and remember a few things about this diagram. The first is the heat reservoir, which gives it an amount of heat Q1. The heat reservoir is at temperature T1. Then we have a working substance. Spelling of working is wrong. Working substance, which is usually a gas or air, which undergoes which type of process? It undergoes a cyclic process, and it gives an amount of work W or delta W out. Do we understand this? Delta Q1 is the amount of heat taken from the source. Delta W is the amount of work that has been done by this cyclic process. Then you have sink. This is the exhaust of your bike or your car. It gives an amount of heat delta Q2 out. This is known as the cold reservoir or sink, which is at a temperature T2. This is how the three things are related. Delta Q1, which is the amount of heat taken, is equal to delta Q2 plus delta W. If you don't want to write delta, is okay. This is what you must remember. Whatever heat we are taking, tung Q1, W1 or W part goes away. It is converted into work, and rest of the heat is going out. Do we understand this? Okay, now from this equation, you can also understand the Kelvin-Planck statement. What was Kelvin-Planck statement? Kelvin-Planck statement told us that there cannot be a heat engine which can convert entire heat into entire work. Please mark my words. Kelvin-Planck statement is no heat engine can convert entire heat into entire work. So basically, Kelvin-Planck statement is telling us that this Q2 amount of heat which is released out, this amount of heat cannot be equal to zero. Do we understand this? Delta Q1 or Q1 cannot be equal to W. You cannot convert entire heat into entire work. Some amount of heat has to be given out. This is Kelvin-Planck statement. Do we understand this? Then we understand the efficiency of a Carnot, efficiency of a heat engine. Efficiency of heat engine is work output divided by heat input. So it is W, which is the work, divided by Q1, which is the heat. Work is Q1 minus Q2. From this equation, we have got this. That can be written as T1 minus T2 divided by T1. This is the work done for a Carnot cycle. What is a Carnot cycle? We will see that. Don't worry. So efficiency is 1 minus Q2 by Q1 into 100% or 1 minus T2 by T1 into 100%. For a Carnot engine, Q1 by Q2 is T1 by T2. What is this Carnot engine and what is this Carnot theorem? We will do that. Don't worry. Right now, just note this thing down. Can you note this down? Whatever I've written, each and every word should be point-wise. Do not mark it in the sheet. It will not serve any purpose. I'll give you a minute to note this down. Have we noted this down? Now, this cycle that you see is known as a Carnot cycle. This cycle that you see is known as a Carnot cycle. This is given in your sheet. Mark it down in your sheet. You may not have to draw it, but understand what is a Carnot cycle. This is a Carnot cycle. This is a Carnot cycle. As you can see, this Carnot cycle starts from point A. Do we all see this point A? Then it goes from point A to point B. This is an isothermal expansion. Do we see this? In this process, the gas is expanding. Yes or no? Do we understand this? This is the process in which heat is taken in. Then from B to C is adiabatic expansion, ADE. AD stands for adiabatic, E stands for expansion. Do we understand this? Then from process C to D, it is it is isothermal compression. Upar wala is expansion, niche wala is compression. Then the fourth process is D to A, adiabatic compression. Do we understand this? This is the temperature of the source. And this is the temperature of the sink. Do we understand this? Just draw this in your sheet. This is a Carnot engine cycle or a Carnot cycle or a Carnot reversible engine cycle, whatever you call it. This is this. It consists of two isothermal process and it consists of two adiabatic processes, two expansion processes, two contraction processes. And remember, I will give you some important points about Carnot cycle. You will have to remember this and never, ever forget it in your lives. I'll give you a minute to win it. Have you noted this down? Now is the time, since we have seen Carnot theorem, we must also understand what is, see, we've seen Carnot cycle, we must understand what is the Carnot theorem. Now, Carnot theorem, from your sheet, it is a theorem that states that efficiency of any reversible heat engine cannot be greater than or equal to the efficiency of a reversible heat engine based on Carnot. So the efficiency of a Carnot engine or a Carnot cycle between any two given temperatures is same. The efficiency of this Carnot cycle, two isothermal process, two adiabatic process, the efficiency of this Carnot cycle or Carnot engine is maximum. You cannot create an engine which has more efficiency than a Carnot engine. Do we understand this? The efficiency of a Carnot engine is the highest. No engine in this universe can have efficiency more than the Carnot engine. Do we understand this? Please note this down. I'll give you a minute to win it. Have you noted it down, bacha? Then just write these important points about Carnot cycle or Carnot engine. Number one, it is an ideal cycle. This is an ideal cycle. This cycle is not possible to create. Why it is not possible to create? It is only a theoretical cycle. You cannot create a practical Carnot engine. Why you cannot create a practical Carnot engine? Because it has two isothermal process and it has two adiabatic process. And remember, an ideal isothermal process is not possible. Similarly, an ideal adiabatic process is not possible, and hence this Carnot cycle is a pure theoretical concept. It's an ideal cycle that cannot be put into practice. Do we understand this? The efficiency of Carnot cycle is maximum. The efficiency of Carnot cycle is maximum. And what is the efficiency of Carnot cycle? 1 minus T1 by T2. Oh, sorry, 1 minus T2 by T1, where T2 is the sink temperature and T1 is the Temperature of the source. Will we remember this? Yes or no? For a Carnot cycle, Q1 by Q2 will be equal to T1 by T2. Will you remember this? These are all the points of the Carnot cycle written, and one of these points will come in your exam. I'll give you a minute to note it down. Have you noted it down, bacha? Great. This was about Carnot cycle. Then we come to heat pump or refrigerator. Heat pump or refrigerator. Now, what do you mean by heat pump or refrigerator? What do you mean by heat pump or refrigerator? What does a refrigerator do? Now, if you look closely on the diagram of a refrigerator, or we may call it as heat pump, this is how a heat pump works. And I hope you can see it on the big screen. You can see this? On the big screen. Now, if you see this on the big screen, does it look familiar to something that we have already discussed? Does it look familiar? This heat pump or a refrigerator, does it look familiar? Can you correlate what is happening here? Now, when we are talking about heat engine, and I am writing this heat engine here, I hope you can see this. When we are talking about this heat engine, what this heat engine was doing, it was taking Q1 amount of heat, then it was doing W1 amount of work or W amount of work, and it was giving out Q2 amount of heat. Do we understand this? That was our heat engine. It was taking heat from a source, it was giving out some work, and it was ejecting some heat out. Now you reverse the entire process. If you reverse the entire process, what will you do? You will take Q2 amount of heat at temperature T2 from a sink. You will take T2 amount of heat. Instead of giving it out, you are taking it in. Instead of work being output, the work is input. This work is the work needed to run the refrigerator. When you put the refrigerator on power, that is when it works. Do we understand this? So instead of work getting output, work has to be input. In case of heat engine, I was taking Q1 amount of heat. Here I am rejecting Q1 amount of heat. So basically your heat pump or your heat refrigerator, or your refrigerator becomes the reverse of heat engine. Understand this or not? The entire thing is the reverse of heat engine, and it is known as a refrigerator. Will you remember this? For a refrigerator, Q2 heat is taken in, absorbed, W amount of work is put in, and Q1 amount of heat is released. I'll give you a minute to note it down. Have you noted this down? Okay. So now we have some corrections in the note. For a refrigerator, Q2 amount of heat is absorbed, work is input in the refrigerator, and Q1 is the amount of heat which is released. Do we understand this? Q2 is proportional to T2, temperature of the sink. Q1 is proportional to T1, which is the temperature of the sink. Do we understand this? Again, we have the same equation, Q2 plus W is equal to Q1. In case of heat engine, we had written it as Q1 is equal to W plus Q2. Q1 was the input and everything was output. Here, Q2 and W is the input and everything else is the output. Do we understand this? Then we had efficiency for heat engine. Here we have beta. This beta is known as coefficient of performance. Do we understand this? This coefficient of performance is heat extracted, how much heat your refrigerator is extracting, divided by how much work you are inputting. Do we understand this? So this becomes your Q2 divided by W. Your Q2 is, your W is Q1 minus Q2. So you can write this formula as Q2 divided by Q1 minus Q2. This is the coefficient of performance for a heat pump. Do we understand this? Do we understand this? Please note this down in your sheet. Have you noted it down? Okay. Now, if I talk about Carnot refrigerator, if I talk about a Carnot refrigerator, in case of heat engine, we had Carnot heat engine. In case of refrigerator, we have Carnot refrigerator. I can write Q1 by Q2 is equal to T1 by T2. Yes or no? Do we remember this? Okay. So the actual formula for coefficient of performance is Q2 upon Q1 minus Q2. This formula is valid for all refrigerators. But for a Carnot refrigerator, the formula can be written as T2 upon T1 minus T2. Do we understand this? How did I get this formula? Because I have put Q1 by Q2 as T1 by T2, and therefore I have the formula for Carnot refrigerator. Can I have some raise hand that we understand this? Okay, please note this down. This is the formula for Carnot refrigerator. This is the formula for Carnot refrigerator. Now remember, friends, all the temperatures that we are using in the formula, what unit this temperature must be? What will be the unit of temperature in the Carnot engine? Remember, the unit has to be Kelvin. Do we understand this? Okay. Let's see if you can do this one. Oops. Yes. A Carnot engine takes heat from a reservoir. This is question number 165. And reject heat to a sink at 27 degrees Celsius. What is the efficiency of this Carnot engine? I hope you understand what we are talking about. This is question number 165. Take it from your sheet. And I'm waiting for your answers. I'll give you a minute to win it. Yes, my dear friends, any answers? A, B, C, D, 1, 2, 3, 4, and the answer is? I can't see. Well, the answer is pretty damn simple. This is a Carnot cycle, Carnot engine. You have to find the efficiency. The formula is pretty simple. 1 minus T2 by T1 multiplied by 100%. They have not multiplied by 100%. Doesn't matter. 1 minus T2 by T1. This is what you got to do it. T2 is the temperature of the sink. T1 is the temperature of the source. You just do it. 1 minus temperature of the sink is 27 divided by the temperature of source is 627. Correct? Yes or no? No, that is not correct because I have used degree Celsius. I should use Kelvin. Yes, yes. Kelvin, 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 Kelvin. Remember Kelvin. Kelvin Planck statement. Kelvin, Kelvin. So this is This becomes 300, my dear friends. This becomes 900, my dear friends. I hope you can do this. The correct answer is C, which is 2 by 3. Into percentage, 100%. If you multiply it by 100%, you will get the answer. Do you understand this? Simple questions. Carnot cycle, Carnot engine, Carnot cycle, Carnot engine, Carnot refrigerator. These are the questions that will come, and this is the next one. Let's see who can crack this. Let's crack it. A Carnot engine operates with source at 127 degrees Celsius and sink at 27 degrees Celsius. The source supplies 40 joules of heat energy. What is the work done by the engine? Oops. Source is giving 40 kilojoules of energy. What is the work done by the heat engine? I'll give you a minute to win it. Any answer, my dear friends? First of all, I have to find the efficiency for Carnot. 1 minus T2 by T1. I hope you can do this. T2 is 300 Kelvin. T1 is 400 Kelvin. 1 minus 300 by 400. 1 minus 3 by 4. It will be coming as 1 by 4. Yes or no? We got this? Efficiency will come as 1 by 4. We got this? Yes or no? Now this efficiency is always equal to work divided by heat input. So this is equal to W divided by Q1. W is the work done. Q1 is the heat. I had given you the note, but you don't seem to recollect it. So it's W divided by Q1. So W becomes Q1 divided by 4. Q1 is 40 divided by 4. Here is the answer, my dear friends. And the answer is... And answer is 210 kilojoules. Do we understand this? Remember the basic formula. Don't forget the basic formula. Don't forget the basic formula, my dear friends. Don't forget the basic formula. Can I move on to the next question? Give you a minute to note this down. And then I'll give you one more question on similar lines. And I hope you can do this. Have you noted this down? But Have you noted this down, bacha? Can you do another question on this? Best of luck. This one comes here. 171. An ideal gas heat engine operates in Carnot cycle between 227 and 127 degrees Celsius. It absorbs 6 into 10 to the power 4 joules at high temperature. That means source. What is the amount of heat converted into work? Your time starts now. Anyone who has done this? Well, how to do this? First of all, we have to find out the efficiency. Yes or no? Efficiency is 1 minus T2 divided by T1. T2 is 400. T1 is 500. 1 minus 4 by 5. 1 minus 4 by 5 is 1 by 5. Do we get this? Yes or no? Efficiency is 1 by 5. Then this efficiency 1 by 5 shall be equal to work divided by Q1. So work is Q1 multiplied by 1 by 5. So basically it is divided by 5. So the answer is 6 into 10 to the power 4 divided by 5. And the correct answer is option number B, option number 2. Do we understand this? I'll give you a minute to note this down. Shall I move on to the next question? This one. And I hope you can give me an answer quickly. A Carnot engine works between the temperature 772 instead of 772 and 27 degrees Celsius. What is the efficiency of this engine? I think it, instead of 772, I think it should be 727. That would make more sense. Just make it 727. Probably that will make more sense. You will have a simple answers. Okay. 772 की जगह make it 727. What is the answer for this one? So it will be 1 minus T2 by T1. T2 here is 300. T1 here is, I think, 1000. 1 minus 3 by 10. That will be 7 by 10 into 100%. The efficiency will be 70%. Yes or no? It will be 1 minus 300 divided by 1000. That is 700 divided by 1000. That is 7 divided by 10. It has to be multiplied by 100. So the answer is 70. Do we understand this? Yes or no? I'll give you a minute to note this down. Let's move on to the next one. The last question for this. And you can see this came in your NEET. An ideal gas heat engine, that means Carnot cycle, operates between 227 and 127. It absorbs 6 into 10 to the power 4 calories of heat. You can understand that the same question comes over and over again. They do not even change the values. Do you see? Have we done this question before? Yes, just now we did it, and the answer is C. Yes or no? That means, and I keep on repeatedly saying this, if you do, there were 170 questions. If you do all 170 of them, if you can, and I have done almost 80, 90 of them, no one can stop you from getting good marks in physics. Again, an inventor claims that the temperature of the source and sink are 127 and 27 degrees Celsius respectively. He's saying that the efficiency of the engine that he has created is 26%. Then you tell him whether he is right or wrong. It is impossible. It is possible. It is impossible, but possibility is less. Its possibility is high. Data is insufficient. Question number 20. He has created an engine that has an efficiency of 26%. The engine operates between 127 and 27 degrees. Is it possible? Is it not possible? And the answer is 1. He is lying. It's an impossible engine to be created. You cannot create an engine of 26% efficiency, beta. Why it is not possible? Because the efficiency of a Carnot engine is the highest. What will be the efficiency of a Carnot engine operating between 127 and 27 degrees Celsius? 1 minus T2 by T1. T2 is 300. T1 is 400. 1 minus 300 by 400. That is 1 by 4. So the efficiency becomes 25%. This is the maximum possible efficiency of a heat engine that can be created between 127 and 27 degrees Celsius. Do we understand this? But this gentleman is saying that his engine has an efficiency of 26%. This is absolutely wrong. This is not possible. Carnot theorem prohibits that. We cannot have an heat engine that has efficiency more than the efficiency of Carnot cycle. Do we understand this? So I will leave the rest of the question. I have completed the entire spectrum of the question that were possible. The second law of thermodynamics is done and dusted. Done and dusted. What is left is some questions on the thermometry part and thermal expansion, which we shall do in our next class. So we will meet in the next class and we will cover the rest of the portion. Take care. Have a good day. If you have any problems, any doubt, please ask. The class is over from my end. Bye-bye.